So at this point here, I'd like to introduce to the stage, we've got Praveen, Otmane, and from Swift, and from Red Hat we have Brian, and they're going to come to stage now and talk about disconnected OpenShift, so a zero-touch provisioning approach with Swift. So without further ado, gentlemen, come to stage. Thank you.
Some introductions. Like I said, I'm Otmane Benali. I'm product owner for a container platform at Swift, and I'm joined by my colleague, Praveen Siddu. He's infrastructure architect, also at Swift. And also we have Brian Ward is a Red Hat OpenShift architect that's been with us for some time, and he helped us in our journey to achieve our goals. And some of it we're going to share with you now. Next, I'll just talk about Swift. I don't know how many people know about Swift. You typically would have used Swift if you did some international transaction payment, then you would need the Swift code. So a little bit more about Swift. Swift is a member-owned cooperative. We provide a global secure financial messaging services. We are used by more than 11,000 institutions and in more than 200 countries. We provide secure, reliable, and efficient financial messaging services. We are literally the global backbone for financial communication. I hope that gives you some introduction. Let's go to the project. Before we start, just to give some background, in our shop, we are managing hundreds of clusters, OpenShift clusters, and we repave our cluster. We don't do in-place upgrades. Our upgrades is rebuilds. We also, everything we build, update, everything is from source, from Git. So it's our source of truth. We can rebuild everything from Git. For this project, what we set out, some architectural goals, and some of them is we wanted to be able to do fast software update, OpenShift software update, as well as operators updates. We want to do fast cluster builds, efficient, consistent. The other thing is zero privilege. We don't want anyone to have access. We want to eliminate access, physical or remote, to any of the clusters. So we will cover that, how we achieve that. So we managed to do that. And obviously, we need to still maintain and achieve our reliability. And most importantly, we need to be able to scale in a consistent way. Some of the results that we achieved is we can now download software declaratively and in this disconnected environment, and we'll be able to promote exactly what we want. We're able to do this from weeks into minutes. We are able to do cluster builds from weeks into 90 minutes. And again, we introduced some other components like this single pane of glass, which is a custom Swift insight that we use for either to get some status that is simple, but also programmatic for doing some automated work. And finally, like I mentioned, we're able to scale. So next, I will hand it over to Praveen, my colleague, to show you how we achieved this.
Thank you, Otmane. We are in a disconnected environment. That means none of our OpenShift clusters are connected to internet. And to download the software, we want to clearly track what images makes as an operator version. We want a clear tracking of what those images were. In the initial versions of OpenShift, we didn't have that ability to download exactly what we need, and it used to take weeks for us to download the software. And from weeks, now we have cut down to just few minutes. For cluster build time, we have, it used to take weeks to build a cluster. Now it just takes 90 minutes to build a cluster. We expanded on that, and now we can build hundreds of clusters and manage hundreds of clusters using the fleet management. All that was possible because of Red Hat's help. We have Red Hat professional engagement. Brian has been with us right from the get-go on this journey. Yasik is one other person, a Red Hat engineer working full-time with us. And they have access to the engineers who contribute to open source, and that helped us put us on the right track, make the good strategic and design decisions right at every step of our way. We are in a disconnected environment. That means users don't have access to the internet. We have only two hosts which has access to the internet, which is rel host and then the Nexus. On rel host, we run a utility called OC Mirror from Red Hat to download the images. The images downloaded are then sent to a local container registry. The list of images that makes a operator version is actually uploaded into Git. This new product that we download, we test in a lab environment, and once we are satisfied, we promote it to dev, QA, and production. And before promoting it, we do use Red Hat ACS to scan the image, and Podman's sign for authenticity, and then Scopio to copy the images. The advantage of Scopio is it retains the hash of the image all along the way when we copy from one container registry to another. We always refer to the images using SHA, so we don't have to worry about tags being moved around. This is a short video. It just shows how so we download software. Is a container operator actually downloading an operator called Gatekeeper. He chooses the product and then enters the version number and enters the channel and clicks on the build button. This initiates a download of the software. It's actually, you can see that it's running the OC Mirror to ensure the inputs given by the user is correct and the version number is present. Once that is done, it just runs the OC Mirror again to download the software, and the software is uploaded to our local container registry. The list of images that makes up this particular operator and version is actually generated by OC Mirror, and it's uploaded to Git. Here you can see that your Red Hat container registry and the SHA-256 of the image, and the list of all the images that makes up this product. And here it's showing in our local registry where the image has been uploaded. And the list of all these images that makes this product is present in Git in the lab branch. And this is what we use to test in our lab clusters. Once we are satisfied, we just promote the image by just copying this list of image, the file from lab branch to dev branch to QA branch, Q to QA to production. That kicks in a pipeline which actually copies the image from the lab registry to the dev registry or QA registry, wherever we promote it. So here is just, once the image has been promoted, we didn't stop there. We wanted to make sure that the image is downloaded and cached in all the geographical locations for that particular environment, so that the image is already available in the container registry before it's made use by a pod spec. Here you can see the image that has been downloaded, successfully downloaded, is uploaded to an object store. The object store is centralized so that we have a clear view of all the environments, and we are sure that the image has already been promoted to that environment before our pod spec actually starts using it. This is about image download. Now we talk about how we build the clusters. It's a fully automated process. Here in this picture, you see a few clusters, hub clusters and app clusters. All of them are OpenShift clusters. The only difference between hub cluster and app cluster is app clusters run application workload. Hub clusters don't run application workload. It just runs Red Hat ACM and Red Hat GitOps. Those hub clusters are used to manage and build and upgrade the application clusters. The configuration to build a cluster is brought in by Argo from Git and made available to ACM. And ACM just uses that to build the cluster. ACM is a very flexible tool. It provides us the ability to build multiple clusters at the same time, because each of those runs its own namespace, and it's containerized, and that's how we can build multiple clusters at the same time. Once the cluster is built, it's just a vanilla cluster. It doesn't have all the bells and whistles. Argo does all the data operations like setting up for LDAP authentication, installing all the operators that's needed before we make the cluster ready for application team to start using it. We also use Argo Vault plugin because we don't, the secrets that's present in Git is just a template with the placeholders for the actual secrets. Argo uses a Vault plugin to pull the secrets from the vault and then apply it onto the cluster. We have health probes running in the environment which keeps the health, checking the health of all the clusters, and it reports the health back to object store, and the object store is centralized. And Swift Insights is a tool custom tool that we built, which can add some business context to it and check the health of all the clusters and make sure that it reports anything any anomaly that it finds. It compares the health of the clusters with the source of truth that's in Git and give us very good insights into what's happening with the cluster. Anytime we make any change to any cluster, we just go back to Swift Insights and see whether something it shows up. If everything's good, then we were sure that the cluster upgrade went good. Here we take a little bit more deeper into how we prepare the cluster and then build the cluster. You can see that Argo is the only entity making changes to the cluster. The human operators don't make any changes to the cluster. The configuration to build the cluster is in a Git repository. So as soon as, and Argo is in auto-sync mode. So any changes that we put into Git actually gets reflected directly onto the cluster. It makes it important for us to make sure that no human users have write access to that repository. As a cluster operator, they would develop new Helm charts, new features, and those features or new operator, those features gets tested in a lab environment. The tested combination of all the Helm charts which make up the entire cluster is then frozen with a version number. Here you can see two version numbers, 102 and 108. And then we run the generate config automation, which actually takes these Helm charts and takes the values which are common to the environment, common to the data center, and values which are very specific to the cluster, and then prepares a fully rendered YAML. This is way different from what others may be doing. We use fully rendered YAML, and fully rendered YAML is in Git. This gives us the ability to see what's going to change in the cluster in the next update, or how the cluster configuration changed in the past 1 month, 2 months. We have clear visibility into how the cluster configuration is changing. It also reduces our need to go and access the Argo UI in production, because we can see what's changing in Git. So we use the power of a programming language like Python and the templating language like Helm, because this is a good combination. So it greatly reduces the complexity of Helm charts, because the values are prepared by Python, and then we run Helm template to actually prepare the rendered YAML files. One last thing to note is we deliberately choose to rebuild, whenever we need to upgrade an OpenShift version, we just rebuild the cluster. We don't do in-place OpenShift upgrade, because rebuild just takes 90 minutes. If Argo is the only entity making changes to the cluster, that means if we have to upgrade one cluster, or if we have to upgrade 10 clusters, it's the same effort, right? Because all we have to do is our work stops as soon as we push the new updates to the Git repository. Argo does the rest of deploying. So if we can manage one, we can manage hundreds of clusters. And that's where fleet management comes in. The fleet management takes in as input the release number that needs to be rolled out and the upgrade strategy. We have some constraints on which clusters can be changed during the weekdays, which can be changed during the Friday, and some can be changed only on Saturday, and some only during a specific window on Saturday. And some clusters may have a change freeze. That means we cannot make changes during the week. So the fleet management takes all this into account while upgrading the clusters. As I said earlier, fleet management just runs in dev. It doesn't need to run in the production, because the job stops as soon as we merge the new content in Git. After upgrading each cluster, the fleet management ensures the health of the cluster is good, and it gives it some soak period, and till that soak period, the cluster health should be healthy. And only then it moves on to the next cluster. Here you can see fleet management in action. The first action is it goes in a loop, upgrading one cluster at a time. One of the safeguard is all the clusters that's already in this new release must be in a healthy state. If any one of them is not in a healthy state, just stops. And then if everything is in a healthy state, it moves on to the next cluster, prepares the configuration for it, and Argo does the rest of upgrading it. Once that is done, it just gives it some soak period and just continues with the next. This gives us a complete hands-free way of managing the clusters at scale. There are certain operations which require us to go to production and execute certain operations. So something is really wrong. The network, there's some issue with the network. We need to run some TCP dump, or we need to run some must gather source report or something like that. One of our goals was not to give any kind of access to cluster operators into any cluster, because that reduces our security posture, right? So we were quickly able to put a UI where a cluster operator has access to only a user interface, not to the clusters. So we use OpenShift pipeline. It was very easy for us to implement that. So pipeline, it just exposes a UI and cluster operator can just choose from the menu what operations that he needs to execute, and then clicks on the button, and the operation is performed on the cluster. And the list of who performed which action on which cluster and when is actually retrieved by another deployment running in the same namespace, and then it's uploaded to object store. So we have clear tracking of who executed which operation on which cluster. And for reusability, we don't use Tecton task. We just use a Python modules just for reusability. Just launch one container where all the modules that's need to be reused is just a Python module. Here you can see the who performed which action on which cluster available in the OCP insights. We have clear tracking for auditability reasons. The third column shows that the operation that's being performed, and the fourth shows who performed it and at what time it ended.
Thank you, Praveen. So just to summarize, the takeaways are we use a GitOps model and use ACM, Advanced Cluster Management, to have faster cluster builds, and of course we improve the software downloads as well, and an OpenShift operator, OpenShift software and OpenShift operator updates. We also introduced fleet management to improve our, to scale our cluster builds or updates and whatnot. We introduced some components that helped us along the way, like Swift Custom Insights and so forth. Zero privilege implementation helped us to meet our requirement regulation as well as security requirements. And finally, we have achieved significant cost savings, and we have improved that time to market by several factors. Okay, and that's basically it. And I'll pass on to Brian if I missed anything. You want to add?
No, I'd just like to point out that this engagement really started around IPI and automation and using Advanced Cluster Manager about a year ago. And prior to that, you guys were building everything with user provisioned infrastructure, and you had sort of cobbled together some automation to build virtual machines in vSphere and to apply configurations. So the process from getting from there to here has been tremendous in what you've been able to achieve in just a 1 year period.
Right, yeah.
That's correct, yeah. Thank you.
Fantastic. Well, thank you for such an engaging session. Do we have any questions at all for Praveen or Otmane? As always, we have a couple of microphones there. I've got a gentleman over the back there with his hand up.
When you say you are monitoring the health of your cluster, right? When you do the upgrades or anything, what if one of the applications that is running in it has some issues? So did you guys categorically identify what constitutes a healthy cluster so that you can proceed to the other environments? Because you said if health of one of the cluster with new release is not good, it will halt everything, right?
Yeah. So for health monitoring, actually, currently the fleet management takes into consideration the health of all the Argo applications. And we have alternate monitoring through our ELK stack to make sure that if there is no memory or disk related issues. But the fleet management just takes into account only the health of the Argo as of now. We're going to build more health probes, like one of the health probes that we are currently building is persistent volume, making sure that persistent volume is functional. So those kind of health probes we are building as along the way. It's a continuous journey for us.
We've also had some discussions around using Lua a scripting language to specifically customize the health check that Argo is running against a specific application as well.
Yeah.
So I know Yasik's implemented that or been working on that.
Yeah.
How you can restore PVPVCs, like, if you don't do in-cluster upgrade, how you can migrate those? And even the traffic, if you have hundreds of clusters, how are you going to manage the cluster, traffic migration from old cluster to new cluster?
Let's take the first question, the PV migration. Before we rebuild the cluster, the first thing is we run an automation which backs up the PV specification, because we use vSphere CSI, VMware CSI for our persistent store as of now. We are exploring other CSIs as well. Currently, we are just using VMware CSI. So we back up the PV definitions to object store before we tear down the cluster. Once we rebuild the cluster, we restore those definitions so those PVs latches onto the same volumes that was existing before. So the application will start off from where it left off before we rebuild the cluster. And we also tell the application team to quiz the application before we back up the PVs. And once we restore the PV, a new cluster is built and we restore the PVs latches onto the same volumes, then the application comes back and just deploys their deployment, and it's pretty simple after that.
Okay. And also, you said, you use the OC mirror to render the files and then upload it via environment. Instead of doing that, you can just use multiple repos and have each repo for each environment, and OC mirror directly uploads the new software to the harbor instead of you do it in a GitOps fashion. Is there a particular reason for that?
All our environments are disconnected, so there's only one utility which has connectivity to internet. And this is, in a lab, we test a combination of images. We want to take the tested combination, the same tested combination all along through our environment. We don't want to download something fresh.
Okay. And you have that HA proxy, the networking between the clusters. How you gonna manage it, like between one cluster to the another cluster when you have a new release? Is that it's just a simple switch, or even the OCP routes, any internal data, when you have a new cluster, the route will be a different one. So all these are managed externally.
Good question.
No, go ahead. Basically, when we rebuild the cluster, we're not changing the identity of the cluster. We maintain the network, the PVs, all the configuration gets restored from Git. We keep exactly like it is. It's transparent to the application.
The subnet used by the cluster, the routes used by the application, the DNS names, everything remains the same. It's just the cluster is down for 90 minutes during this rebuild time. And
I think you might want to point out that you load balance across multiple clusters in different regions as well.
Yes.
So there's not a concern about the application's availability.
Yeah, application availability is active is running in multiple regions. And the one where we do the rebuild, basically we took it down for this kind of detached volumes, rebuild and then restart everything.
Yeah, but the application is active in the other data center during this rebuild time.
No, that's great. Hey, I think we've got time for one super quick question.
This is, hopefully this
don't want to
is
hold you up
simple.
from the coffee break, folks, but these questions are great.
You'd mentioned CoreOS in your thing. Did you have trouble getting CoreOS through an enterprise requirements or a security screen? Because it said CoreOS is your base OS for the clusters. Is that?
Yes, that's right. In OpenShift, I think that's the only option. CoreOS is the only option, yes.
Thank you.
Okay, fantastic. Well, Praveen, Otmane, thank you very much.
Thank you.
Thank you.
Much appreciated, guys. And a big shout out to Brian as well, so thank you.